If you take a golf club and let it swing about freely by attaching it to a shaft, when you drop it 90 degrees from vertical, the club swings down like a pendulum and can hit a ball placed on a tee across the room and hopefully into one of these cups. But the question is, which cup? Welcome back to Engineered Bets. The expected launch distance is 2.6 meters or 8.5 feet, which is about as far as your friend's average tee off, and this center cup has been placed accordingly, surrounded by an arbitrary formation of cups, and it's your job to guess which cup the golf ball will land in. Keep in mind, any bounce shots or bank shots are fair play. To estimate the velocity of the club at the bottommost point, the conservation of energy was used, but since the mass of the club is distributed unevenly, the center of gravity was first determined by finding the point on the shaft where it can balance on my finger. I marked this point with tape and found that it's roughly 0.76 meters from the point of rotation, including the PVC coupler. Finding this point lets us treat this complex pendulum like a simple pendulum where all the mass is concentrated at this point. Setting the lowest point to be y of 0, the club's center of gravity starts at 0.76 meters, and that potential energy can be converted into linear kinetic energy, which is 1/2 mass times velocity squared. The linear velocity for circular motion is equal to the angular velocity, aka the rate the object is rotating, times the distance from the point of rotation. Since I'll use the angular velocity for the next part, I'll substitute this equation in for the velocity. Anyway, solving for this angular velocity, and the club should be rotating at 5.08 radians per second or 291 degrees per second when it reaches this bottommost point, right before hitting the golf ball. To analyze the collision of the club with the golf ball, the conservation of angular momentum was first used. Just before the collision, the club's angular momentum is its moment of inertia times its angular velocity, which we just solved for. Since the golf ball is at rest right before the collision, it has no initial angular momentum. Then, right after the impact, the club will still have some angular momentum as it swings through, which will again be its moment of inertia times its final angular velocity, which is currently unknown. After the collision, the golf ball will now be moving, so its angular momentum will be its linear momentum times the distance from the point of rotation. Since the ball will actually be launched at an angle due to the slope of the club face, you need to multiply this term by the cosine of the angle the ball will be launched at to only get the component of linear momentum acting perpendicular. Based on a quick Google search for a 7-iron golf club, and I found that it should launch at about 16 degrees. We've now got one equation, but two unknowns. We don't know the final angular velocity of the club, and we don't know the launch velocity of the ball. So we need to use another piece of information to solve this. Just like the bouncy ball video, I'll use the coefficient of restitution in place of the conservation of energy to account for energy losses caused by inelasticity. Based on another quick Google search, I estimated this coefficient to be about 0.82 for a collision between a golf ball and a club. The coefficient of restitution is a ratio that compares the final club and ball velocities to the initial ones. If there were no energy losses, this coefficient would just be 1. Anyway, the initial velocity of the ball is 0, so this term is gone. The final velocity of the ball is what we want to solve for, so I'll leave it as is. For the final and initial club velocities, I can use the angular velocity times the distance from the point of rotation, but then I need to convert it to only use the component that goes through the axis of the collision, which again will be cosine of the launch angle. Solving for the final angular velocity in terms of the ball's launch velocity and then plugging it back into the conservation of angular momentum, and we've simplified it down to just one unknown, the launch velocity of the ball, which we can solve for by plugging in all the known values to get that it should be launched at a velocity of 7 meters per second. With this velocity, the final step would be calculating the trajectory of the golf ball. The ball's not going to travel that far, it's not launched that quickly, it's pretty heavy and somewhat small, so I don't know that drag's going to play a huge role, but I'm going to factor it in anyway since I've ignored it a lot in previous episodes. Starting with the vertical or y direction, there's the force of gravity pulling down on the ball and the force of drag opposing its movement. Since the ball initially moves up, the drag will be acting downward, so I'll make this a negative, but it's worth noting that this sign will need to change once the ball starts falling. Normally plugging in the velocity would account for this, but since it's squared, the directionality is lost. Anyway, that's a conditional I'll account for later, so let's just continue and solve for the vertical acceleration, plugging in all the known values, the acceleration due to gravity, the mass of the golf ball, the standard density of air, the ball's cross-sectional area, and lastly the drag coefficient, which for a golf ball I estimated to be about 0.5, although it does seem to vary based on how fast it moves. After simplifying, you see that the acceleration is of course not a constant, but rather a function of the ball's velocity, which is changing, so I'm going to solve this differential equation numerically, just like in the video with the toy parachute. The ball will be launched from a height off the ground that happens to be the same height as the lip of the cup, so I'll just define that to be y of 0 to make things simple. So it starts from 0 meters off the defined ground and will end at 0 meters. We also know the initial vertical velocity by taking the sine of the launch velocity found in the last part. plugging that value into our equation, and we get the initial vertical acceleration to be negative 9.85 meters per second squared. Next, we'll assume the ball accelerates at this constant rate for a short period of time, let's say 0.1 seconds. Later, we'll check that this time step is small enough to minimize the numerical error. Next, since we know that the acceleration is the rate at which the velocity is changing with respect to time, we know that the integral of the acceleration, aka the area under this acceleration step, is the change in velocity, which comes out to a decrease of 0.98 meters per second, which we can then subtract from the initial velocity to get the next velocity value. Likewise, since by definition the vertical velocity is how the vertical position changes with respect to time, we can do a similar integral or area under the velocity curve calculation to get how much the position changed during this step. Now, to continue this cycle, we use the new calculated velocity to estimate the next acceleration, which then lets us get the next velocity, and therefore the next position, and so on and so forth until the height reaches 0. One thing I already mentioned but should point out here was that as soon as the ball had a negative velocity, meaning it's falling instead of rising, the sign of the drag term in the acceleration equation was changed to a positive to account for it now acting upward on the ball. Anyway, doing this all the way until the ball hits 0, aka the cup of the lip, and we've got our choppy approximated solution. To smooth this out and reduce the numerical error, I'll decrease the step size to half of what it was before, and after performing twice as many calculations, it looks a bit smoother. But I'll decrease it again 50 times further down to 0.001 seconds, and now we've got a great looking numerical solution that approximates the analytical solution that you could have gotten if you actually did the complex integral of this equation twice. Anyway, we can now see the ball will hit the red solo cup 0.39 seconds after launch. The acceleration looks like a constant value, so the force of drag didn't play much of a factor here, and I probably could have just used kinematics, but maybe in the horizontal calculation it will matter more. Anyway, to calculate the horizontal distance that the ball will move in this time, I'll do the exact same thing but in the horizontal direction, and since this video is already getting quite long, I'll just skip through this quickly since I already outlined the steps. The only difference is that in the acceleration equation, the only force acting horizontally on the ball is drag. So we've got our horizontal acceleration equation, the ball starts at x equals 0, we use cosine this time to get the initial horizontal velocity, which can then be used to get the initial horizontal acceleration, and then using a time step and iterating through, you get the choppy solution, and you can already tell there's basically no acceleration, so I definitely could have ignored drag, which would have saved you about 2 minutes and me about 7 hours, but at least we saw the steps through in case it did matter. Lastly, decreasing the step size to refine it, and you can see that after 0.39 seconds, the ball will have traveled 2.6 meters or 8.5 feet. So that's how the distance was approximated, and this center cup was placed accordingly. I filled up these cups with water to hopefully get the ball to land and stay in one of the cups without knocking them all over. Here's a final look at what the swing looks like towards the bottom, and this isn't perfect form, so to make sure it went straight, I did a small test swing and it seemed to land on the black tape, so hopefully it's aligned well enough. Anyway, pause now to predict in the comments which cup the golf ball will land in, and welcome back to those of you who skipped here to the end. No shame there, best of luck to all of you. With everything set up, it's now time to see what actually happened. After what I'd say was a pretty clean strike of the golf ball, the ball shot pretty straight and just barely missed the front cup, bouncing off the rim. It then bounced off the back wall and barely missed the back right cups before bouncing again and finally ending up landing in none of them. Congrats to those who got it right, and that's a bad beat for those who guessed the front cup. I've decided to run it back to see if this janky setup is at all consistent, and on the second attempt, the ball landed in almost the exact same spot, this time knocking the front cup over. I'm honestly surprised this janky setup worked so well, and the analysis seemed to barely underestimate it, although it could be a combination of overestimating and underestimating things that makes it get closer to the outcome. Let me know in the comments which factors you think contributed the most. I'm still looking for more sponsors of this series, and this video didn't have one, so if you have the means or the desire to support, consider purchasing my 2 Truths and Trash trivia deck. It's based around the other show I make, and it's 50 science trivia cards where 2 of the statements are true and the other one is false, and it's your job to guess which one that is. It's a pretty cool car ride or campfire activity in my opinion, and there's lots of interesting things you'll learn along the way. Anyway, thanks for watching to the end, and I'll see you next time.